Welcome to Surveying and Geospatial Insights, the podcast that maps the technologies shaping our profession. I'm your host, Survey Steve. For centuries, surveying involved the painstaking process of measuring discrete individual points. Today, we are in the era of reality capture, where we can measure not just points, but entire environments in breathtaking detail. The technology at the forefront of this revolution is LiDAR. So today we're taking a deep dive into LiDAR data capture methods. We'll explore how it works, the different platforms we use to deploy it, and the best practices that ensure quality results. Joining me is my colleague, geomatics technology expert Debora. Welcome.
Thank you for having me, Steve. It's an essential topic because LiDAR is no longer a niche technology. It's a core competency for the modern surveyor. But having the equipment isn't enough. The true skill lies in knowing which LiDAR method to apply to a given problem and how to execute the data capture with the rigor and discipline that our profession demands.
Let's start with the fundamentals. Debora, what exactly is LiDAR?
LiDAR stands for light detection and ranging. At its core, it's a remarkably simple and elegant concept. The LiDAR unit emits a pulse of laser light. That pulse travels through the air, hits an object, and a portion of its energy reflects back to the LiDAR sensor. The system has an extremely precise clock that measures the round-trip travel time of that light pulse. Since we know the speed of light is a constant, we can calculate the distance to the object with the formula. Distance equals the speed of light multiplied by the travel time divided by 2.
That's a great explanation of the fundamental principle, but I know there are different kinds of LiDAR systems. Could you touch on the main types a surveyor might encounter?
Broadly speaking, there are two main methodologies: time of flight and phase shift. Time of flight systems, which are common in aerial and mobile mapping, measure the direct travel time of a discrete laser pulse. They are excellent for measuring long distances. Phase shift scanners, on the other hand, emit a continuous laser beam with a known wave pattern. They then measure the subtle shift in the returned wave pattern to calculate the distance. Phase shift scanners are typically used in terrestrial applications, as they are extremely fast and can achieve very high precision over shorter distances.
And it's not just doing this once. A modern LiDAR scanner is doing this up to 2 million times per second. By combining that distance measurement with the precise angle at which the laser was fired, the system can calculate a three-dimensional X, Y, B, coordinate for every single point it measures.
Exactly. The result is what we call a point cloud, a massive, dense collection of millions or even billions of individual measurement points. Each point in that cloud has a coordinate and often additional attributes. One is intensity, which is the strength of the returned laser pulse. This can help differentiate between materials. For example, asphalt absorbs more light and has a lower intensity value than a painted road stripe. Many LiDAR systems also integrate a camera, allowing us to assign a true color or RGB value to each point, creating a stunningly realistic, photorealistic 3D model.
This technology is incredibly versatile, which is reflected in the different ways we deploy it. Let's talk about the three main LiDAR platforms, starting with the most precise: terrestrial laser scanning, or TLS.
Terrestrial scanning is what most people picture when they think of high-definition surveying. The scanner is mounted on a stationary tripod, just like a total station. From this fixed position, it rotates and scans its entire surrounding environment. Because it is static, it can achieve the highest levels of accuracy and point density, often measuring points with millimeter-level precision.
This makes TLS ideal for applications where detail is paramount. Think of creating as-built models of complex industrial facilities like power plants or refineries, where every pipe and valve needs to be located precisely. It's also used for historic preservation, monitoring the deformation of dams or bridges, and for forensic mapping of crime or accident scenes. The challenge, of course, is that from any single viewpoint, there will be shadows or areas occluded by other objects. So, a typical TLS project involves performing multiple scans from different locations and then registering or stitching those individual point clouds together into one cohesive model.
And that registration process is a survey-grade procedure in itself. It's not just an automated button click. A surveyor will use control targets or sophisticated cloud-to-cloud algorithms to precisely align the scans. They will then analyze the registration report to ensure the statistical fit between the scans meets the project's tolerance. It's a critical QA/QC step to ensure there are no systematic drifts or blunders in the final combined point cloud. You have to prove that the model is a single, geometrically correct entity. That's the workflow. But what if your project is not a single building but 100 miles of highway? That's where the next platform comes in. Mobile LiDAR Systems, or MLS.
With mobile LiDAR, the scanner is mounted on a moving vehicle, typically a truck or SUV. To be able to map accurately from a moving platform, the LiDAR sensor is integrated into a sophisticated system that includes a survey-grade GNSS receiver to determine its position on the Earth, and critically, an inertial measurement unit, or IMU. The IMU is a device that uses gyroscopes and accelerometers to measure the vehicle's orientation, its roll, pitch, and yaw hundreds of times per second. By combining the position from the GNSS and the orientation from the IMU, we can calculate a precise trajectory for the vehicle, which allows us to georeference every single laser point that the scanner emits while in motion.
The primary advantage here is efficiency. You can capture vast amounts of data for linear corridors like highways, railways, and utility networks, all while traveling at normal speeds. This improves safety by keeping surveyors out of live traffic and dramatically accelerates project timelines. The accuracy is typically in the range of a few centimeters, which is more than sufficient for design-grade topographic surveys and asset management.
So we have static on the ground with TLS and moving on the ground with MLS. The final platform takes us into the sky, aerial LiDAR.
Aerial LiDAR operates on the same principle as mobile mapping, with an integrated scanner, GNSS, and IMU, but the platform is an aircraft. Either a traditional airplane or helicopter, or increasingly, an unmanned aerial vehicle or UAV. Manned aircraft are used for large-scale mapping, capturing data for entire states or counties, often for floodplain mapping or forestry management. UAVs or drones operate at a much lower altitude, which allows them to capture incredibly dense point clouds for smaller, project-specific sites like construction progress monitoring, volumetric surveys of stockpiles, or detailed corridor mapping.
A key advantage of aerial LiDAR is its ability to penetrate vegetation. A single laser pulse leaving the aircraft might hit the top of a tree canopy, and some of its energy reflects back. But the rest of the pulse continues downward, hitting a branch, and then, finally, the ground. A sophisticated aerial LiDAR sensor can record all of these returns. This allows data analysts to classify the point cloud and algorithmically strip away the vegetation points to create what we call a bare Earth model, a highly accurate digital terrain model of the ground surface, even in a dense forest. This is a capability that no other technology can match.
So, we have these three powerful platforms, but great data doesn't happen by accident. It requires a commitment to survey best practices, starting with mission planning.
Absolutely. The most important step of any LiDAR project happens before a single laser pulse is fired. You must clearly define the project objectives. What is the required accuracy and point density? What specific features need to be captured? What will the final deliverables be? The answers to these questions dictate which platform is appropriate, how the data will be collected, and how much survey control is needed.
Let's talk about that survey control. This is the part that grounds the cool technology in solid measurement science. For a TLS project, this means placing specialized targets throughout the site and coordinating them with a total station or GNSS to a known coordinate system. This ensures that when you register the scans together, they fit perfectly and are correctly georeferenced.
For mobile and aerial systems, it means setting out distinct ground control points, or GCPs, across the project area. These points are not only used to help process the trajectory and lock the point cloud to the project datum, but they are also used as independent checkpoints. We compare the known coordinate of the checkpoint to the coordinate derived from the point cloud. This gives us a statistically valid assessment of the final data quality and is a critical part of any professional deliverable.
Another best practice is ensuring sufficient data overlap. For TLS, this means planning your scan locations so that each setup has a clear view of targets or features from previous setups. For mobile and aerial systems, it means planning drive paths or flight lines that overlap significantly. This redundancy is key for a robust solution and for eliminating any data gaps or shadows behind obstructions.
To bring it all together, LiDAR technology has given surveyors an unprecedented ability to model the world in 3D, but the technology itself is only a tool. The choice of the right platform, whether static terrestrial, dynamic mobile, or from the air, must be driven by the specific demands of the project.
And ultimately, the quality of the final product rests not on the scanner, but on the surveyor. It's our expertise in mission planning, our diligent establishment of survey control, and our rigorous quality assurance procedures that transform a simple point cloud into an authoritative and reliable geospatial dataset.
A perfect summary. Debora, thank you for shedding some light on this powerful technology. And thank you to our listeners for joining us on Surveying and Geospatial Insights.